Welcome back to The Explainer. Today, we're doing something wild. We are pushing gravity to its absolute breaking point, just to see what happens to the fabric of reality. Now, we all know Einstein's general relativity, right? It is incredibly successful at predicting how stars and planets move. But what happens when you take that brilliant, beautiful math and push it into the absolute most extreme environments in the universe? What actually happens when the literal fabric of space-time is stretched completely beyond its limit? Well, let's dive right into this by asking the ultimate cosmological question about the dark centers of black holes, and really the limits of general relativity itself. Standard physics tells us that right at the center of a black hole, gravity becomes infinite, and bam, we hit a singularity. But look, nature absolutely abhors an infinity. A singularity usually just means, hey, our math broke down here, and we're missing a deeper, more fundamental truth about how the universe actually operates under catastrophic stress. So here's our roadmap for today. We'll start with number 1, when classical gravity breaks down. 2, the discrete spacetime substrate. 3, the corrected field equation. 4, pathways of deformation. 5, the cost selection algorithm. And finally, 6, surviving extreme gravitational regimes. All right, let's jump right into part 1, when classical gravity breaks down. First up, we really need to understand exactly where Einstein's incredible equations finally hit a brick wall. See, general relativity assumes space-time is this smooth, continuous sheet. Think of it like a perfectly woven trampoline. But as it turns out, that smooth continuum, it's just a macroscopic illusion. When you zoom way, way into the Planck scale, which is literally the absolute smallest measurable length in physics, that smoothness completely shatters. Theoretical frameworks like unified dynamics suggest space-time is actually discrete and pixelated. And when you hit those pixels, the smooth math of classical gravity completely falls apart. Which brings us to part 2, the discrete space-time substrate. So if space-time isn't a smooth rubber sheet, what exactly is it? What are the actual pixels of the universe made of? Well, I want you to think of this substrate as a discrete network of nodes and edges, constantly passing information back and forth to literally build the geometry of the universe. The source material calls this simplicial, discrete, informational spacetime. Don't let the big words scare you. Just imagine it not as an empty room where things happen, but as a dense, buzzing computer network. It's a foundational packet routing lattice that forms the actual structure of reality. Everything, geometry, matter, the whole shebang, emerges from how information is transported and routed within this specific network. And here is where it gets really cool. The crucial point is that gravity isn't just a curve in an empty void. It's actually the physical congestion of this informational traffic network. When heavy objects, like stars or planets, exist in this network, they act like massive data loads. They clog up the transport lattice. So when information tries to route around these massive loads, it takes more steps. It takes a lot longer. And that detour tax, the literal extra effort required to cross the congested network, is exactly what you and I experience as the pull of gravity. Mind-blowing, right? Okay, moving on to part 3, the corrected field equation. Now, to handle this cosmic traffic jam, the unified dynamics framework has to upgrade Einstein's math. Think of this corrected field equation like an anatomical diagram, isolating exactly where the new structural upgrades live in the math. Einstein's original equation is still in there, and it works perfectly in normal traffic. But unified dynamics adds 4 very specific correction terms, these delta t variables you see here. They represent the precise physical ways the discrete network accommodates the intense strain of heavy traffic. We've got closure angle strain, packet spacing strain, channel slack strain, and branch topology rewiring. These are absolutely crucial. They aren't just mathematical rounding errors. They are actual, physical, structural shock absorbers built right into reality itself. Let's explore those in part 4, 4 pathways of deformation. We really need to visualize how these 4 distinct variables actually behave when we apply extreme gravitational load to the whole system. Think of space-time like a massive bungee dome undergoing an intense stress test. It has 4 specific backup systems to prevent catastrophic failure. When you push down super hard on that dome, it doesn't just snap immediately, right? It yields, it stretches, it bends, it dynamically redistributes the weight. Well, this discrete lattice of spacetime does exactly the same thing using these 4 distinct pathways. Let's break them down, one by one. Okay, so if you push on the network, the very first thing it tries to do is simply bend the angles of its connections. This is the closure angle accommodation. In our ordinary weak field universe, like, say, right here on Earth, this is the dominant pathway. The lattice just flexes smoothly. It's exactly like the soft joints of our bungee dome bending just enough to absorb a light push. And this is why general relativity works incredibly accurately for us, because the overall structure of the network remains largely intact, just slightly skewed. But what if bending just isn't enough? Well, the substrate will literally alter the spacing between the data packets to accommodate the heavier load. This is called packet spacing accommodation. As we get closer to incredibly dense objects, the actual physical distance between the informational nodes in the lattice begins to stretch and compress. Imagine the individual chords of our bungee dome actually stretching out to handle the localized heavyweight. Now we're getting into some really dangerous territory. At this higher level of stress, we're seeing the network dynamically change how much weight a specific channel is even allowed to carry. We call this channel slack accommodation. If a specific path in the network is just utterly overwhelmed with data, the lattice redistributes the burden to adjacent paths. It's like taking tension off a visibly fraying bungee cord and immediately shifting that tension over to the surrounding cords just to keep that whole section from totally giving out. And finally, we hit the ultimate failsafe. This is where the actual topology of spacetime changes its branching structure just to survive. If a connection is under so much extreme strain that shifting capacity around isn't enough, the local network literally snaps that connection and rewires its neighbor relations to form an entirely new, stable geometry. This is branch topology rewiring. It's the absolute most extreme form of accommodation, literally a fundamental restructuring of who is talking to whom in the quantum network. And that takes us to part 5, the cost selection algorithm.
So you might be wondering, how does the universe actually decide which of these 4 pathways to use at any given millisecond? Like, does it always bend, then stretch, then rewire? Well, the absolutely brilliant thing here is that there is no universal rigid sequence. The substrate relies on a cost selection algorithm to constantly calculate the path of least resistance to stay intact. The active deformation is chosen by calculating the cheapest repair cost. The lattice looks at the local stress and deforms along the softest admissible mode. For example, if rewiring a branch is actually mathematically cheaper in a specific high-stress scenario than stretching the packet spacing, the universe is going to rewire the branch first. It's a highly dynamic, self-healing calculation happening instantly, right at the Planck scale.
The sources use this biological analogy that just perfectly captures what's going on. They say the universe actively heals its own topological defects by sequestering them into safer dimensional pockets. Just like a human body starves a tumor by cutting off its blood supply, the spacetime lattice starves catastrophic errors, like a singularity, by actively routing that crushing gravitational data into cheaper, safer channels. It dynamically shifts the massive burden into spatial distance or phase changes way before the defect can permanently destroy the entire network. Let's wrap it up with part 6, surviving extreme gravitational regimes. Let's take everything we have just learned and apply it to the ultimate cosmic test, a black hole merger. When 2 black holes collide, the gravitational burden far, far exceeds what a classical, smooth spacetime could ever hope to process. I mean, the energy released in a fraction of a second is more than the light of all the stars in the observable universe combined. If spacetime were just a smooth sheet, this event would tear a literal hole in reality. So how does our discrete, pixelated network actually survive this? Well, under this kind of extreme stress, the network relies on what the sources call a survival hierarchy. This is driven by eigenmode classification, which honestly is essentially just a fancy way of saying it sorts its repair options by their stiffness. When those 2 black holes merge, the lattice rapidly calculates all these repair costs. Modes with high structural maintenance costs, the stiff ones, are aggressively suppressed. They are totally starved of fractional weight. Instead, the substrate forces the unimaginable burden into the softest modes available, relying entirely on those cheap accommodation channels we just mapped out. And this dynamic, real-time response shows exactly why the universe doesn't just break. It intelligently distributes the catastrophic energy of a black hole merger across its discrete hardware. The lattice yields. It aggressively utilizes packet spacing and channel slack to absorb the massive blow. It rewires its branch topology to maintain containment. What classical physics views as a singularity, a totally catastrophic infinity, this framework reveals to be a highly orchestrated phase transition. The network is pushed to its absolute limit, for sure, but the bungee dome holds. It survives by dynamically rewriting its own geometry. Which leaves us with a profound realization about the true nature of reality, and honestly begs the ultimate question of what happens when the universe reaches its absolute computational limit. We've seen how brilliantly this discrete network manages the incredibly heavy traffic of a black hole merger by finding the cheapest repair pathways. But man, it really forces us to wonder, is there a hard limit to this accommodation? If gravity is just congestion on an informational lattice, could an event ever occur that is so massive, so incredibly instantaneous, that all 4 accommodation channels are exhausted simultaneously? What does a true, completely unrecoverable network crash actually look like in the cosmos? Definitely something to keep you up at night. Thanks for joining me on this explainer. And remember, keep questioning the fabric of everything.